in general, thermodynamics is complicated. And so as we go through this chapter review, I want to build up the lesson so that it becomes more complex as we go along. And so at the beginning here, I'm going to first discuss the simplest system possible. And the simplest system that we could have is what we call a single component system. And so what I mean by that is we're just going to deal with one chemical species to begin with. All right. Now, here, as we go through the lesson, I'm going to use some kind of complex terminology. So at this point, I want to define a few terms that I'm going to say quite a bit. So the first thing I'm going to define is the term phase equilibrium. Right? And so whenever I say this, what I mean is that when we're at phase equilibrium, what we have is the case where the amount of moles of a species in a particular phase is constant. Okay? And so really, just in general, throughout the rest of your academic career, anytime you see the word equilibrium, you should associate that with the word constant. Okay? Because that's generally true. Another thing that we're going to discuss quite frequently is phase diagrams, or are phase diagrams. And so what a phase diagram is it describes, what phase a species is going to be in under various conditions. Okay? And so phase diagrams describe what phase a species will be in under certain conditions. Okay. All right, and so in a little bit, I'm going to go through the phase diagram for water. So this is something you probably saw even back in your general chemistry courses. But as I'm going through the phase diagram for water, what I want you to keep in mind is, the actual experiment that was performed in order to determine this phase diagram. All right? And so whenever we talk about phase diagrams in thermodynamics, they're usually based on systems that were held underneath a piston. Okay? And so conceptually, you should have this in mind. And so in these sort of phase diagram determining experiments, what they did is they basically had a piston set up like this, right? So here is the piston. And so this piston's on top of a container. And underneath the piston is the chemical species of interest. So this is the system. All right? And so by changing the height of the piston, you could change the pressure on the system. And also you could heat and cool the system as well in order to control the temperature. All right? And so whenever we're talking about phase diagrams, think about this experiment, which allows the scientists to control both pressure and temperature. So phase diagrams are typically determined using this sort of piston setup. Let's now go and take a look at an example of the phase diagram for water. Okay? And so these phase diagrams are fairly dense with information. Okay? So I want to go over slowly about the various different features that they offer. The first thing I'm going to highlight are the axes. And so for phase diagrams, they're typically plotted in 2 dimensions, and you could use various different sort of axes to describe the phase diagram. But in this course, the phase diagrams we're going to look at, typically the y-axis here is going to be pressure, and the x-axis is going to be temperature. So this is a PT phase diagram. Okay? Now, in this phase diagram, perhaps the most obvious features are the different phases. And so in this region over here, if you have pressures and temperatures that correspond to that region, the water is going to be a solid. You're going to have ice, okay? And if your pressure and temperatures correspond to this region, your water is going to be a liquid. And if your pressure and temperatures correspond to this region, you're going to have the vapor, all right? And so that's fairly simple and easy to get across. Now, the other main feature that you could probably observe in this phase diagram are these various dark lines that go across here, all right? And so these lines are known as coexistence lines. And the reason they have that name is because at these lines, we don't just have one phase. We don't just have, for instance, over here, we don't just have a liquid or a vapor, but we actually have both, right? And so at these coexistence lines, we have multiple phases that are in equilibrium to each other, right? And so for instance, over here on this line, we have liquid and vapor. If we have pressures and temperatures that correspond to this line, we're going to get solids and liquids. And perhaps the most interesting point on this phase diagram is right here, where we don't just only have two phases, but we have all three. And this point, because we have all three phases, it's known as the triple point. Okay? And so these dark lines correspond to the parts of the phase diagram where you have multiple phases. You'll see as we keep going to the right here that the line just sort of abruptly ends. All right? And so the point where the line ends is known as the critical point. At temperatures past this critical point, we only have gases, right? We're basically at too high of a temperature. So, past that temperature, the molecules have so much energy that it's not possible for them to form a liquid again. Okay? Now, this critical point, it's determined, the pressure and temperature where it occurs is the PC and TC. And so these are the same critical pressure and critical temperatures that we used when we calculated the compressibility factors back in Chapter 5 for our non-ideal gas law. Okay? And so at these different pressures and temperatures, we have different phases that exist. But perhaps the most interesting thing is, if we remember, these phase diagrams were determined using these sort of piston experiments, is that if we change the pressure or the temperature in the experiment, we actually undergo a phase change. So for instance, let's say we start our experiment so that the pressure and temperature in the system correspond to this point A. All right? And so at point A here, we just have a vapor, right? All of the water is a vapor. But then, let's imagine, and so I'll draw out just to visualize this a little bit better. Let's imagine the system looks like this. All right? So that's what it looks like at point A. Now, let's imagine that we then lower the piston on the system so that it starts to squeeze the system a little bit more. And by squeezing it, it increases the pressure to point B. All right? And so, but at the same time, we're keeping the temperature constant. And so we only change the pressure. When we do that, we get to a point B here such that the pressure is so high that instead of just having a vapor, we start to see little liquid droplets form. Right? And in fact, it starts to rain inside of the piston. And so that's because by increasing the pressure to this point, we start to hit the coexistence line in the phase diagram. Right? So it starts to rain inside the piston. And then if we increase the pressure even more, we get to the point where there's absolutely no more vapor in the system, and we only have liquid. And so at this point, I'll draw the piston again. and our system is underneath here. And now we just have liquid water. Okay, then now let's say we keep the piston the same height so that the pressure is the same. But then we just start to heat up the system. Right? So we go from point C to point D here. We heat the system so much that the liquid then gains enough energy to evaporate. Right? And now we start to have both liquid and vapor in the system. And if we keep heating it more, all of the water molecules will have enough energy to form the vapor. And then we just get back to having vapor in the piston system. Okay? And so that's, as we navigate through the phase diagram, we could start to see that our chemical species could transform from one phase to another. The last thing I'm going to point out on this phase diagram, in particular at the coexistence line between the liquid and the vapor, is that at that coexistence line, so let's focus on point D here. At this coexistence line, the pressure that corresponds to the coexistence line is going to be the vapor pressure of water, P star, and the temperature that corresponds to that coexistence line is going to be the boiling point temperature. All right? And so at a pressure of 760 millimeters of mercury, which is 1 atmosphere, right? The boiling point temperature for water there is 100 degrees C, right? So that matches what we see in real life. But if you were at a lower pressure, so let's say you're at 17.535, right? Your boiling point would be much lower. It'd be just a little bit above 20 degrees C. So phase diagrams are dense with information. And so I'm just going to write down and try and summarize a couple of main points that I talked about when I was going through the phase diagram. Okay? And so at the coexistence line, or lines, right, our single chemical species, even though we just have one chemical species, it exists in 2 or more phases. Okay? In the coexistence line, we have that critical point in which if you're at a temperature higher than the critical point, you only have a gas. So the critical point occurs at PC and TC. Okay, and for the line between the liquid and vapor phases, the pressure of that line corresponds to the vapor pressure, and the temperature at that line is the boiling point temperature. Okay? And so even though that phase diagram was just for water, the things that I wrote down here are true for any chemical species and its phase diagram.